Hi everybody, hope your day is going well. Our essential standard is I understand, can find, and can justify concavity, this is curvature, as well as inflection points. We have a couple of pictures here. The first one has a graph, or at least a portion of a graph, where it's concave upward. What concave upward means, it means that our derivative f prime is going to be increasing. It means that our second derivative is going to be greater than 0. The second derivative is going to be positive. Again, as I said earlier, please try to avoid when you're using descriptions to justify stuff, the words increasing or decreasing. Students typically do those wrong. Try to focus on the positive or the negative with the appropriate other analysis. One of the things for concave upward means that our graph is going to be above our tangent lines. And so if you look over here at all our tangent lines, say for instance this line over here, this graph is going to be above the tangent line. Concave downward means that our first derivative is decreasing. It means that our second derivative is going to be negative. Our graph is going to be below our tangent lines. And again, if we want to think about what it means for the first derivative to be decreasing, this slope over here might be something like 8. This slope over here might be something like 1. This slope over here might be negative 4. And as you go from left to right, your slopes are decreasing. That's going to be concave down. So the concavity, the graph of f of x is concave upward, or just concave up on an interval, if your second derivative is greater than 0 on the interval. It also means that the first derivative is increasing on the interval. But again, as I said just a couple of minutes ago, please, when you're doing your explanations, focus on first derivative or second derivative being positive or negative, and you will have far more success with those particular items, because that's what you're actually doing when you're doing your analysis. The graph of f of x is going to be concave downward on an interval if the second derivative is negative on the interval. It also means that the first derivative would be decreasing on the interval, but again, try to focus on the positive or the negative. When we're going to talk about concavity and approximations, this will show up on your AP test. We're going to cover this concept more thoroughly in a later lesson, but again, just kind of look through the logic of this. A tangent line approximation will underestimate the value of the function if the function is concave upwards on the interval used by the tangent line. And if you look over here at this particular tangent line, notice that the graph is always above that tangent line. If I'm using the tangent line to make an approximation, say at this x coordinate, that y value that I get would be less than what the true y value is, and my approximation would be an underestimate. Going the other direction, if your function is curved down, and we have, say, this tangent line over there, approximations made with that tangent line are going to be overestimates. If you have a particular x value, say over here, and you use the tangent line to approximate, that y value is going to be an overestimate. It's going to be bigger than what the true y value is. Again, an easy way to figure this out, or at least visualize this, is take your hand and curve your hand, and then take your other hand and put it flat. It's like, ooh, look, it's too big. It's an overestimate. Or if you take your hand and curve it the other way, and then put your other hand underneath flat, it does help. Obviously, you can't see me with this. Hopefully that helps. Hopefully at some point we're back in person where you can see that visual. And so our first problem we come to is they want to know on what intervals is this function concave upwards, and they want us to justify our answer. And again, with a lot of these problems, the difficult work is actually finding our first derivative and our second derivative. So let's go about trying to do that. We could do a quotient rule in this particular problem, but this particular problem will be a lot easier doing a chain rule. I can rewrite this as a negative first power, the x squared plus 12 to the negative first power. And so my derivative over here is going to be this negative x squared plus 12 to the negative 2 power times the derivative of what's inside, which is going to be 2x. This first derivative over here is going to be this negative 2x divided by x squared plus 12 squared. This is only the first derivative. I got to find the second derivative to identify if something is concave up or concave down. And so we're going to go and find our second derivative. In order to do this, I'm going to need to do a quotient rule. It is the denominator, this x squared plus 12 squared, times the derivative of the numerator, minus 2, minus the numerator, which is going to be positive 2x, times the derivative of the denominator, which is going to be a chain rule. Take the 2 in front, decrease the exponent by 1, multiply by the derivative of what's inside. This is all going to be over my denominator squared. Squared squared is going to be the fourth power. I have to try to simplify this. What works well is try to figure out what's going on with the different terms. In the numerator, you have two terms. You have a term over there, and then you have another term over there. Both of these have an x squared plus 12 in it, and there's an x squared plus 12 to the fourth power in the denominator. And so I could divide the entire numerator as well as the denominator by x squared plus 12. This fourth power is going to become a third power. The first power is going to become a 0 power, so that one's going to go away. And the second power over there is going to become a first power. At this point, I have my second derivative. I can take my negative 2 and multiply it through the yellow part. I get this negative 2x squared minus 24. For the blue part over there, I have a 2x times a 2 times a 2x. That over there is going to be an 8x squared. And this is all over the x squared plus 12 cubed. Combining like terms, this is going to give me a 6x squared minus a 24 all over this x squared plus 12 cubed. Let me look real quick. Yep, that looks good. And so at this particular point, I have my second derivative. This second derivative is never undefined. The x squared plus 12 will always be 12 or bigger, but this does equal to 0. When does this equal 0? When the 6x squared minus 24 equals 0. We can factor that. There's a 6 in common. There's this x squared minus 4 that's left over. And this is going to give me this x is equal to plus or minus 2. Those are the two numbers that would make that equal to 0. And so if I try to analyze this, I have two numbers that are important. I have this negative 2 and 2. I'm analyzing my second derivative. I'm analyzing f double prime. And I'm going to be looking at this expression over here for f double prime. What is going on in each of these intervals? Is it positive or is it negative? And so if I look at this, my denominator will always be positive. It's going to be at least 12 cubed always. And so I really only need to worry about my numerator. If I pick a large magnitude number, either positive or negative, and I plug that in, the 6x squared is going to dominate, and you're going to end up with positive values for both of those. If I plug in a number like 0, the numerator is going to be negative 24, and you're going to get a negative value. They want to know when this is concave up. And so this is going to be concave up, or concave upwards, from negative infinity all the way to negative 2, and from 2 all the way to infinity. The endpoints will never be included. They don't meet the definitions. Finally, they want us to justify our answer, and we can say something like this. On these intervals, f double prime of x is greater than 0. Okay, the next thing we come to is something called an inflection point. We have some little diagrams up here indicating when things are inflection points or when things are not inflection points. For an inflection point, if the second derivative of a function is 0 or undefined at a point, there's a possibility of a function having an inflection point at this point. Just like when the derivative is equal to 0 undefined at a point, there's a possibility of a maximum or a minimum, but there's no guarantee. You do not have to have an inflection point when the second derivative equals 0 or the second derivative is undefined. In order to get an inflection point, there has to be a change in concavity, either concave up to concave down or concave down to concave up. And this doesn't really show up in AP Calc, but does show up later. And the function has a tangent line at that particular point. And so over here, if you look at our graph, we have a tangent line that would do something like this. We have a tangent line that would do something like that. We have a tangent line that would do something like that. And we have a graph that changed from curved up to curved down. We got an inflection point. A graph that changed from curved down to curved up. We got an inflection point. A graph that changed from curved down to curved up. We got an inflection point. Even though with the next graph, it does change from curved down to curved up, because there's no inflection point, because there's no tangent line at that particular point, there's not going to be an inflection point. Again, in this class, it doesn't really show up. They don't push that concept hard as far as AP goes. What they typically do in this class when they write stuff out is they talk about these functions being twice differentiable. And if you have a function that's differentiable or twice differentiable, it means that you're not going to have a sharp point. You're not going to have either a corner or a cusp, and you will get a tangent line. And so what they basically do in this class, your logic that they want you to get to is inflection points occur where the second derivative changes sign. Even though there's also the additional requirement that you have to have a tangent line at that point, they don't actually look for that in AP Calc. They just look for that you understand that the second derivative changes sign. Okay. They want us to find all the points of inflection for the function f of x, 3x to the fifth minus 5x to the fourth, and they want us to justify our answer. Inflection points occur where the second derivative changes sign, so we got to go and find our second derivative. And we're going to get that this f prime of x is going to equal 15x to the fourth minus 20x cubed. Your f double prime of x is going to equal 60x cubed minus 60x squared. We would like to find out when this changes sign. It's not about when it's equal to 0, it's when it changes sign. But in order to do that, we're going to set this equal to 0 and find our numbers where it could potentially change sign. And so there is this 60x squared in common. What's left over? There is this x minus 1 that's left over. And so I end up getting that either x is equal to 0 or x is equal to 1. If I go and analyze my second derivative, I have these two critical points, 0 and 1. And I want to try to figure out what's going on for this particular second derivative on each of these intervals. If I plug in a number like -1, this particular expression is going to be negative. The 60x squared will always be positive, and the x minus 1 is going to give us negative. If you plug in a number between 0 and 1, you're also going to get negative. And if you plug in a number bigger than 1, like 2, you're going to get a positive times a positive. It is going to be positive. Notice over here that 0 is not an inflection point because my second derivative did not change sign. I did not have a change in concavity. But the x equals 1 is an inflection point. And so we're going to get an inflection point at the point 1 comma something. How do I find the something value? I'm going to take this value and plug it into my original function. If I do that, I get 3 minus 5. I'm going to get -2. So 1, -2 is an inflection point. It's an IP. They also asked me to justify my answer, and so what I'm going to do, say the following, at this point, f double prime changed sign. In order to get an inflection point, you have to have a change in sign, and we do have that change in sign there. And that is going to be my justification. Okay, the next question, it comes from the 2015 question number 5, parts B and C. It was a no calculator question. The figure to the right shows the graph of f prime, the derivative of a twice differential function f on the interval between -3 and 4. The graph of f prime has horizontal tangents at -1, at 1, and at 3. The areas of the regions bounded by the x-axis and the graph of the f prime on the intervals between -2 and 1, and 1 and 4 are 9 and 12 respectively. So this area is 9 and this area is 12. We don't know what that means yet. Stay tuned. We will hit that in chapter 4. On what open intervals contained between -3 and 4 is the graph of f both concave down and decreasing? And they want us to give a reason for our answer. And so what is the meaning of concave down? Concave down means that our second derivative is negative. And so I got to find all the regions where that second derivative is going to be negative, is going to be less than 0. How do you find the second derivative given the first derivative? Well, it's going to be the derivative of this. And so what ends up happening is in this particular interval between -3 and -1, the slope of f prime, which is the derivative of f prime, which is the second derivative of f, it's going to be negative. Similarly, between 1 and 3, this particular second derivative is going to be less than 0. It's going to be negative. Again, the derivative of the derivative is second derivative. Derivative is slope, and on these portions of the graph, the slope is negative. Now they're asking about decreasing. What does decreasing mean? Decreasing means that my first derivative is less than 0. And so I have a graph of first derivative, and my first derivative is less than 0 when the y values are less than 0. And so over here on this region from -2 to 1, my first derivative is negative, and from 1 to 4, my first derivative is negative. Now they're asking me for where are both. They want both. And so where's the overlap between this? And so our intervals are going to be from -2 to -1 and from 1 to 3. These are the intervals where the graph is both concave down and decreasing. They want us to give a reason for our answer. We're going to say something as follows. On these intervals, f double prime is less than 0 and f prime is less than 0. That's our reason. Part C, they want you to find the x-coordinates for all points of inflection for the graph of f, and they want us to give a reason for our answer. And in order to find an inflection point, we have to have a change in concavity from concave up to concave down and vice versa. We just said that the yellow regions are concave down. Where are the regions that are concave up? And so if I want to find concave up means that my second derivative is greater than 0. How do you find the second derivative? It is the derivative of the first derivative. In this particular case, the derivative of the first derivative is going to be the slope on this particular graph. So in this particular region, my graph is concave up, and in this particular region, my graph is concave up. Do I have any locations where the graph changes from concave up to concave down? Yes, right over here at -1, it changed. Right over here at +1, it changed. And right over here at 3, it changed. And so we're asking for just the x-coordinates, and we're going to get that x is equal to -1, +1, and +3. And let me erase those lines. It's a little bit easier to read the numbers without the lines on there. But -1, +1, and 3. Again, in this particular region, we had a negative second derivative, then it went to positive second derivative, then it went to negative second derivative, then it went to positive second derivative. They're asking us for a reason for our particular analysis, and we're going to say this. They want us to find all points, and so we should give some type of generic disclaimer that we've looked everywhere. Say something like this. These are the only points where what? Where f double prime changes sign. That's the reason why we get an inflection point, our second derivative change sign. This last one over here, I think it's the last one. Yep, it is the last one. This is your turn. We'll read it together and I'll let you guys work on it. The figure above shows the graph of f prime, the derivative of a twice differential function f on the closed interval between 0 and 8. The graph of f prime has horizontal tangent lines at 1, 3, and 5. The areas, the regions between the graph of f prime and the x-axis are labeled in the figure. The function f is defined for all real numbers and satisfies f of 8 is equal to 4. On what open intervals contained between 0 and 8 is the graph of f both concave down and increasing? Explain your reasoning. So give that one a shot and see if you can figure it out. Welcome back. They want concave down. What does concave down mean? It means that your second derivative of your function is going to be less than 0. They want increasing. What does increasing means? It means that your first derivative is going to be greater than 0. This over here is the first derivative, and whenever this first derivative is above the x-axis, it has positive values. In this particular region, in this particular region, and in this particular region, my first derivative is positive. This is the graph of the first derivative, and whenever the y-coordinates are positive values, it indicates that your first derivative has a positive value. Remember, we don't see the graph of f. This is the graph of slopes. Concave down means the second derivative is negative. And so in order to find the second derivative from the first derivative, we got to find the derivative of this graph. That over there is going to be slope. In this particular region from here to here, my slope, my derivative of the first derivative is going to be negative. In this particular region from here to here, my slope, my derivative is going to be negative. And that is the only regions. Everywhere else, the function is going up. So where do we have overlap? Where are they both true? And again, they asked us to do what type of intervals? They asked us to do open intervals. So do open intervals, answer the question asked. And we're going to say basically 0 to 1 and from and from 3 to 4. But those are the two regions where they're both true. They ask us to explain our reasoning, and we'll do something like this. On these open intervals, what's true about this? F double prime is less than 0, and F prime is greater than 0. Oops, really want to circle everything. Again, I hope our lesson made sense. These graphs of derivatives are super important. They're not going to go away. We're going to keep doing them the rest of the year, pretty much on every single test going forward. And so make sure that you understand these graphs of derivatives. If you need some help, please reach out to me, and I'll do my best to help.